Okay, this section's on collision theory, section 12.5. Alrighty, so let's just start with some ideas behind collision theory. These ideas are actually pretty straightforward and sensible when you think about them. So first of all, the first one is that if things want to react, then they must actually collide, that is, contact one another. That makes sense, right? Things don't react at a distance, which makes a lot of sense. The reactants, they must collide in the correct orientation, which again makes sense, and I'll give you an example in just a moment with the diagram below. And the last one is that the reactants must have sufficient kinetic energy in order to overcome their activation energy, and I'll talk about activation energy as I progress through this lecture. All right, so let's give an example of how this would work. We've got this molecule here, which is carbon monoxide, reacting with oxygen here, O2. So in this case here, I hope you can see that the carbon monoxide is the oxygen banging into, its oxygens banging into the other oxygens of the oxygen molecule here, and that's actually not the correct orientation for the reaction. If you look down to the next one, you can see this is the correct orientation, and then as you could see, because you've got CO2 where the carbon's in the middle here, it would make perfect sense. It has to be this orientation. So that's obviously a successful collision. So one thing, that it's got to collide. Two, they've got to collide in the correct orientation. The last one is they've got to have sufficient energy, kinetic energy, that is energy of motion, in order to overcome this thing that I've called, or people call, activation energy. Okay, so let's have a little bit of a think about temperature. Temperature actually measures the amount of kinetic energy of particles, molecules in a system. And what does this mean? Well, what this means is if you increase the temperature, it makes sense. The reactants, okay, they've got to collide. And if you increase the temperature, things move much more, and so therefore you would expect more collisions. In fact, when you do all the calculations, what you find is that's indeed the case. You do get more collisions, but the amount that you get isn't that much, actually. Okay, we already know this one. The reactants must collide in the correct orientation, and I'm just pointing this out because really temperature doesn't increase the proportion of correct collisions because it's a random event. So I mean, obviously it increases the number, but not the correct orientation. And the last one, if you remember that previous slide there, reactants must have sufficient kinetic energy, that is energy of motion, to overcome this thing called activation energy, which is actually the requirement for to drive the reaction forward. And when you increase temperature, that actually significantly increases the proportion of reactants with sufficient kinetic energy. That basically, the rule of thumb is basically if you increase the temperature by 10 degrees C or Kelvin, doesn't really make any difference because it's a relative increase, you will actually double the reaction rate because you're actually doubling the number of the proportion of reactants that have sufficient kinetic energy to overcome this thing called activation energy. So let's flesh this out a little bit more using this classic thing, the activation energy diagram. Over here we're plotting potential energy of the system versus here the extent of the reaction, and some people call this the reaction coordinate. In other words, how the reaction's progressing. So if we think about two reactants here, what happens is they come together. If they've got sufficient energy, they move up to a state called the transition state energy, which is kind of like the transition state is kind of an intermediate between what the reactants would look like and what the products eventually become. So here's an example here. I put in the one before about carbon monoxide reacting with the oxygen. That's the transition state. Now, that transition state has always got a much higher energy than the reactants and the products, and so we can actually, if we know what the energy of the reactants is going to be, and we can measure the energy of the transition state, we can actually work out the difference between them. That's the activation energy there. So that amount of energy is the energy that needs to be overcome by the kinetic energy of these reactants to flow through the transition state and down the other side to the products here. The other term that I just want you to be aware of is this one, the change in heat, which we'll later, in fact we'll do it now, we'll refer to as enthalpy. The reason for that won't become apparent for a while, but that's the enthalpy of the reaction, which is basically the change in heat of the reaction at constant pressure. So and so that's the amount of energy you get out when you or heat energy when you're actually carrying out a reaction. So up here I've got some notes for you. I've talked about the activation energy. I've talked about enthalpy, what the extent of the reaction is, and what the transition state represents. And there's also a nifty little YouTube video there with an animation that I suggest you watch. Okay, so what proportion of molecules actually, here we go, of a lot, oh no, there it is. What proportion, no, I have lost it. And now it comes back when I do that. That is so weird. Okay, so what proportion, no, I have lost it. So what proportion of molecules have sufficient energy to overcome the activation energy? Well, the answer to that is here. I'm going to have one more try at getting this pen. It's not going to let me do it. No, won't let me do it. Okay, so what proportion of molecules have sufficient energy to overcome the activation energy? Well, on the left-hand side of this graph here, we've got the number of molecules. Down the bottom, we've got the kinetic energy. And we've got two temperatures here represented, T1 and T2. So let's look at T2 first. So in the case of oh no, we won't, beg your pardon. We're going to look at T1 first. So in the case of T1, what I want you to notice here, so T1 is at a lower temperature than T2. I want you to notice here where this tail is, where it says EA. So that's the energy of activation. That is the activation energy of a particular reaction. So what this is really saying to you is anything that is equal to or above that activation energy, that is that shaded area there, represents molecules that have sufficient energy to overcome the activation energy and for the reaction to occur. Now in the case of T1, I hope you can notice that there's a shaded region there which changes when you go to T2. That is, with T2 is higher, this curve kind of gets squashed down a little bit, and the proportion of molecules that actually have more activation energy is increased. I think you can see there that roughly you could say probably about double. It's about double the proportion of molecules. So that means that that temperature's gone up sufficiently that there's quite a lot more molecules that have that activation energy so the reaction can proceed. Okay, so you don't, I put this maths in here, you guys don't really need to know this, but I just thought I'd put it in for interest's sake. The bottom line is when you increase temperature, a lot of people think the main reason why a reaction goes, like increases its rate is because the molecules are jiggling around a lot a lot more, and that increases the rate on the collisions. But if you do the calculations, the bottom line is, and I've given you an example here, if you increase the temperature by 10 degrees from, say, 20 degrees Celsius to 30 degrees Celsius, the number of collisions, or I should say the velocity, which is proportional to the number of collisions, only goes up by about 1.7%. So it's not very much. So something else is going on there, and what's going on is what I was talking about before. A lot of that effect of temperature and increasing reaction rates is actually increasing the proportion of molecules with that higher activation energy. And you can see it in these equations here. Now, again, you don't have to know anything about these equations, but I'm just putting this in here so you get a bit of an idea of what's happening. The rough rule of thumb is this, is if you increase the temperature by about 10 degrees Kelvin, it actually doubles the reaction rate. And when I say 10 Kelvin, I actually also mean 10 degrees Celsius, because it's a change in temperature, and the two are exactly the same thing in terms of a change. And you can do the calculations to show this is the case. So here the reaction rate here has gone up to this value. It's in fact doubled now, right? Because the temperature's gone from, as you can see here, from 20 degrees C to 30 degrees C, and the reaction rate's doubled. Now, contrast that with previously, and you can see that the reaction rate in terms of collisions, just that rate would only go up by about 1.7%, a couple of percent, whereas here it's actually doubled because of that. Okay, so what are the practical applications of collision theory? First one's this. Now, this actually explains a huge number of phenomena, right? So, for example, you know that matches aren't going to burn unless you strike them, or indeed unless you heat them up sufficiently. And the reason for that is because you need the reactants to achieve that activation energy in order for the reaction to proceed. TNT reacts more violently than gunpowder. The reason for that is that TNT, the actual molecule itself, is the reactants. And so everything is very, very close together. All the reacting species are on the same molecule. And so because they're so very close together, they can collide very, very efficiently. And so the reaction can proceed much more quickly. Now, that's not the case with gunpowder, because classic black powder gunpowder actually consists of potassium nitrate, sulfur, and carbon separately, then ground up as a mixture. So it's not actually, the reactants aren't on the same molecules, they're actually on completely separate species, and so therefore they can't react anywhere nearly as quickly as what TNT can. It also means that under the right conditions, if you get the reactants well mixed so that they can react quickly with one another, that is, they can collide easily with one another, you can get the crazy situation where things that normally you wouldn't expect that could blow up indeed can blow up. So a classic example would be something like a sugar refinery. It can blow up very quickly indeed because of what happens is you get granulated sugar. It gets there's a dust of sugar that's created. That dust is very fine. It mixes with oxygen in the atmosphere, so the reaction can proceed really, really quickly. Another one would be, as you well know, petrol tanks generally don't explode, and the reason they don't is because the reactants are indeed petrol and oxygen, and so therefore you have to get a good mixture of both before they can indeed explode. You chew your food precisely for the reason of trying to get the reactants mixing well. And so again, that increases the number of available collisions and the rate of the reaction. Fatty foods, those fatty foods, they don't solubilize well in water or at all, and so therefore the only way you can get reactions to occur with fats is often just to use a detergent. The detergent that we use is called bile salt. You can stop fire using a fire blanket. Clearly, there's a fuel. You want to restrict the amount of the other reactant, which is oxygen. And of course, on a hot, windy day, bushfires become an extreme problem because that wind is actually blowing the major reactant, one of the major reactants, that is oxygen, around much more quickly. It's making it much more available for a reaction, and of course it's hot as well, which means as the temperature goes up, the proportion of reactants can actually react as much higher to overcome activation energy. And last one, I've got mercury fulminate. That was the main primer used in things like rifle cartridges, etc. As you know, all you need to do is for a hammer to strike the primer in a cartridge, and then that will cause an explosion. The reason for that is because mercury fulminate actually has a very, very low activation energy, and so therefore you only need something as minor as a hit with a hammer in order for it to explode, which then causes the main charge in the cartridge to explode. Okay, that's it for that one, and now we'll go on to catalysis.